This is bread. We can see loads of bubbles trapped in this network of something. So what is this something? So you may be wondering, what the fuck is this? But this is actually a model for bread made with spaghetti, hazelnuts, peas and blue tack. What do these things represent? These long spaghetti strands here represent glutenin. The peas represent gliadin. They're the two proteins in bread, and together they form gluten. So that's actually what gluten is. It's a group of proteins, so glutenin and gliadin. The hazelnuts, these are starch. And the blue tack, what's that? Well, it's called a disulfide bond. So it's a strong bond that forms between glutenin strands. One thing this model leaves out is the water and the gas bubbles, but I'll show the gas bubbles later. So we're assuming that there's water mixed in here. So what is gluten development? So when water is added to flour, it hydrates the flour, and this allows these disulfide bonds to form. So let's just have a look at glutenin and the disulfide bonds and see why they are so important. So if we just isolate this glutenin strand here, if there's a force on that strand this way, so for example if we're stretching dough, then it's going to get pulled in this direction, and it's relatively easy to do that. However, if the flour has been hydrated and we have disulfide bonds formed, so for example with these three glutenin strands, so now what's going to happen when we start pulling on this strand? Remember that these disulfide bonds are really strong. So if I start pulling on this strand, instead of just this glutenin strand moving, I'm also pulling these three strands as well. And it's going to be much more difficult because these will get caught on other things around here. So instead of just this strand, I have to move this whole structure, or I have to break these bonds. So put enough force into this to break these strong bonds. In either case, I have to put a lot more force into this. So in the case of a dough, it means I have to, if I'm stretching the dough, it means I have to pull a lot harder to stretch the dough. This means overall that the more disulfide bonds that there are, the stronger the dough will be. So that's how the physical properties are linked to the disulfide bonds. And how do we create more of these bonds? Well, as we mix the dough, the glutenin strands will come into contact more often. So as we're mixing, this one might come to here, they get close enough and form a bond there. And then say up here, these two might get close enough to each other to form a bond. And so as we mix, we just create more and more of these bonds and the dough gets stronger and stronger. So that's what gluten development is really. Just bear in mind that this model is sort of shown with the strands going left to right, but you'll also have strands going up and down as well. So let's take a look at the gliadin. What does that do? These only bond weakly with the glutenin. So the bonds between that and glutenin is way weaker than the disulfide bond. The way to think about them is they act like ball bearings. So they kind of stop the glutenin strands from getting close enough to each other to form a bond, which means that the more gliadin we have, the fewer disulfide bonds we're going to get in the dough, because the gliadin are just preventing the glutenin strands from getting close enough. What this means in the dough is gliadin makes the dough more extensible, which means that it's easier to pull apart. It's less strong. And what about the hazelnuts, the starch? Well, starch just kind of sits there and absorbs water. As we're baking the bread, these heat up, and as these heat up, they absorb water and swell until they can't hold any water any longer because they just get too big, and then they'll burst and release starchy gel into the bread mixture. In this model, I haven't included water or gas bubbles, but we would have big gas bubbles in there. So these would sort of sit inside like this, the glutenin strands wrapped around them. The reason the gas bubbles can't escape is because they're just wrapped in a mesh made of this stuff. So they're just trapped in like that. So one thing I want to talk about is what happens when we shape bread. So this is sort of what the structure looks like at the start when we haven't really shaped our bread dough. But what happens as we manipulate the dough and shape it is these glutenin strands tend to straighten out and form kind of a mesh structure. And now if we try to stretch this structure, because it's a mesh, it's much more difficult because we'd have to stretch the whole thing rather than just individual glutenin strands. So that's how our dough develops strength, is it forms this like mesh structure. Let's try to understand why different flours behave differently. One of the factors which is very important is the ratio of glutenin to gliadin. So let's say we have very few gliadins. What this means is that there's very little blocking the glutenins from bonding to each other with these disulfide bonds. So you're going to get a lot of these bonds. So with a dough, this feels like a dough which is very strong and not very extensible. So it's difficult to stretch out far. And that's because there's loads of these disulfide bonds which you are pulling against. However, if we have a lot of gliadin, what this means is it's very difficult for the dough to form these disulfide bonds because the glutenin strands can't get close enough to each other. Another way of saying this is there's a low density of disulfide bonds. What this means is that the dough is not that strong and it's very extensive, so you can pull and stretch the dough fairly easily. A third factor on how strong the dough feels is just the protein percentage, which is essentially the percentage of these gluten and gliadin in the dough. Let's say that this model represents a bread dough, which has been made with a flour with a high protein percentage. Now I'm going to transform it into a pastry tart dough, which would have been made with flour with a low protein percentage. So as you can see, there's just fewer glutenin and gliadins, and that means that by ratio there's more starch in there. The lower protein percentage means that there's fewer disulfide bonds and weak gliadin bonds. That just means that the dough is going to be easier to pull apart and it's going to be less chewy. So the next time you eat a pain au chocolat, you'll know exactly what's going into your mouth. Thank you for watching. If you enjoyed this video, then there's many more. Just click above. If you're interested in delving deeper, I've done a pastry course that's available now. Just look in the description for information.